Hello everyone, this is Sabir Bhai, Analog and Mixed Signal IC designer, founder at Analog Brain, and this is our lecture 6. In this lecture, we'll derive the MOSFET small signal model in presence of CLM completely from scratch, and we'll also identify the proper region of operation for a MOSFET. So in this lecture, we'll actually derive the small signal model, number one. Number two, we'll find the constraint on small signal approximation for a single MOSFET. It means when the small signal approximation would be valid, okay? And the second thing, we'll identify the region of operation for a MOSFET to be an amplifier. Then the last will do some simulation in Cadence to see uh, how can we plot uh, region. Okay, so in y-axis we'll plot region of the MOSFET, and in x-axis we'll vary our first port and second port variable like VGS or VDS, and see what happens to the region. Okay, so let's begin. So we already know that our second port current is nothing but ID. So it is actually I2, second port current, and our second port voltage is VDS, which is actually your VDS. So, and we also see in our next lecture how the graph looks like. Okay, so the graph actually look like this. For ideal thing, we can say the graph will look like something like flat. So in that thing, we can say our y22 is equal to 0. It means your RDS is infinite. You have infinite output impedance. So this is for ideal. But in reality, in your simulation, you will see that a slope like this. Okay, because of channel length modulation. So you have lambda is not equal to 0. It means your y22 is not equal to 0. So this is the real thing. So now we want to model our small signal from that thing, and we'll model for this. And the thing is, uh, how we can model with from scratch. From scratch, we can use Taylor series to model this behavior. We already know for ideal one, our ID is for ideal one. We can say for ideal one, our ID is nothing but half mu n Cx W by L, then VGS minus VTH whole square. Okay, but for real one, we can see that this whole thing will appear at here. Okay, then we'll also have some 1 plus lambda VDS. Okay, so for the ideal one, we can say ID is a function of only VGS, your first port voltage. But for real one, we can say that ID is a function of VGS and VDS. Okay, so now how you can model that? Okay, let's simply think about a scenario. Suppose we have a MOSFET here. Okay, this is our MOSFET, our NMOS, and this thing is grounded, and I'm assuming that the MOSFET is properly biased. Okay, but properly biased, but it is biased and it is on, but uh, I'm not telling for it is in triode region or saturation region. I'm not guaranteed you, and I'm not also telling that your small signal model is only valid for saturation region. It is valid for every region. Okay, so uh, until your signal is small. Okay, so let think that it is in saturation. Okay, and uh, you have your biased. Okay, now we have to apply a small signal. Okay, so let's apply. So this is a small signal, so you will have a variation in your first port voltage VGS. Okay, and you will have something like this in your second port voltage. Okay, so this is some small variation. You can tell this small variation as VGS, and this is some small variation which is actually VDS. So overall you have VGS small v capital GS. It actually means your bias VGSQ, your bias point. Okay, VGSQ, and your small signal VGS. Okay, this V is same. Okay, so small v sub capital means total effect, and this is your quotient point or your bias, and it also applicable for VDS also. Okay, so for VDS, VDS, you can say this is nothing but VDSQ plus a small v small ds. Okay, so now uh, let's write your condition id is equal to f of VGSQ VDSQ. So I am talking about only the bias, no signal. Okay, we have no signal, only have bias. So idq, your quotient drain current, will be your function of VGSQ comma VDSQ. Okay, so let's think that this is our equation 1. Okay, nice. So now let's think about the total effect. So our total effect will be a small I capital D. It means IDQ, this one, plus your small signal current produces by this small signal voltage variation, and this will be a function of what, this small small v capital GS and this small v capital DS, or we can write simply VGSQ plus small VGS comma VDSQ plus small VDS. Okay, nice. So now we can apply Taylor series to equation 2. This is our equation 2. So let's apply. So according to Taylor series, you can write f of VGSQ comma VDSQ, okay, plus your variation small VGS. This is your variable. Okay, so this will be dou ID over dou VGS, and this differentiation should be happened on a single point, and this point is your operating point or quotient point. This is VGSQ comma VDSQ. Okay, nice. So now this is a actually this is a multivariable function. We have learned for single variable function, also multivariable function. So you just apply your single variable function for this twice separately, and it is very easy. Okay, now so this is a small VDS, again dou ID over dou VDS, again it should be in your operating point VGSQ VDSQ. Okay, so that's our first term. Let's write our second term. Our second term would be VGS square, small VGS square divided by 2 factorial dou square ID dou VGS square, again on your operating point VGSQ comma VDSQ plus small VDS square by 2 factorial again, and it will be dou square ID, your second order differential equation. Okay, second time dou VDS square plus you can write for your third term VGS cube by 3 factorial dou cube ID dou VGS cube VDS cube by 3 factorial. Okay, dou cube ID. So let's move on from that thing. So this is your equation. Now I'm assuming that our VGS is equal to V in our input small signal is very small, and uh, its limit VGS tends to 0. You can also write like that, limit VGS tends to 0, or it have some constraint. Okay, so it is small. So if it's small, we can say one thing, that this VGS ID dou VGS this term will be greater than this VGS square by 2 factorial. Okay, and if it's greater than this uh, second order term, then it will be greater than all its like all of its higher order terms. Okay, and also it's true for this. So we can neglect all of the higher order terms if our VGS is small. If our VGS is small, then our amplified VDS version, it will also be small. Okay, then we can say that we can assuming it like f of VGSQ times VDSQ plus small VGS dou ID over dou VGS times VGSQ. Okay, VGSQ plus VDSQ, and this term small VDS dou ID dou VDS. Okay, nice, VGSQ times VDSQ. Okay, so this is our third equation. Now what next? So see this thing, this is our first equation IDQ, and this is our third equation. This is actually your IDQ plus ID. So what will happen if we minus this third if we minus this first one from this third one? Okay, actually we want to model uh, the small signal. Okay, so we want this ID, only this ID. We are assuming we are properly biased. We are not want this large bias anymore, IDQ. So just simply minus this IDQ from this IDQ plus ID. Okay, let's see what happened. We have this thing. Okay, f of VGSQ VDSQ here. So this term and this term will be cancelled, and we left with this VGS and all over that thing. Okay, so let's see, go to next page. So we actually have this thing, your small id is equal to nothing but VG VG sorry, VG. Now we have VG dou ID over dou VGS around the operating point VGSQ and VDSQ plus VDS dou ID over dou VDS again around your operating point VGSQ VDSQ. Okay, nice. We have our equation for our small signal current ID, small I small d. So now let's focus on this equation. What is this thing? This is a voltage and this is a current, and in the left side this is a current. So this should be a current and this should be a current. Okay, now this is port 1 voltage, your VGS. Okay, this is your VGS, port 1 voltage. But this thing dou ID over dou VGS, VGSQ, VDSQ, this thing is a slope, you already know. Okay, but this current uh, is from second port, but this is from your first port. Okay, so this is not a resistor, you can call it a voltage controlled current source. Okay, so let's think that you have a drain, this is your drain and this is your source. Okay, but and you have a drain current, you have a drain current like this, and this drain current is ID, and it has two separate paths. Okay, for this one VDS dou ID over dou VDS, we can simply tell that this current is related to this drain and source, so this is nothing but a resistor. Okay, so this is a resistor, this is a resistor. So now this dou ID, this is a resistor, this is drain, this is source, so this is VDS, this is plus minus, this is VDS. So whatever this quantity, we already know, if this is a resistor, this will follow the Ohm's law. So we already know Ohm's law, I is equal to V by R. Okay, so this thing is nothing but a resistor. So we can model it like that. This is 1 over dou ID over dou VDS. Okay, but what about this thing? This is a drain current, but your voltage is not from this port, drain and source. Your voltage is from another port. So your current is actually controlled by a voltage. Okay, and this voltage is not from here, from another part of your circuit. So this is nothing but your voltage controlled voltage source. So let's write it. So this is a voltage controlled voltage source. Okay, so this voltage controlled voltage source is controlled by a voltage called VGS, but it has a coefficient. Okay, and this is like this dou ID over dou VGS. Okay, now we already know this is nothing but your GM. Okay, and here is your gate terminal, so here is your VGS. So congratulations, we already derive our small signal model for our MOSFET, and this will now look like this. we have our GM VGS. So this is our GM VGS, and we have our output resistance or drain to source resistance. We can call it RDS. Okay, and this is your gate, so this is your VGS. This is your drain, this is your source. Nice. So now we can actually tell all that thing. We already said that your Y21 is actually your GM dou ID over dou VGS around your operating point. This is very important, VGSQ, VDSQ. So it means that this uh, when you are writing your drawing your small signal model, yeah, you actually write GM VGS, but this GM not comes from small signal analysis. This is from your bias, from your DC operating point. Okay, your DC operating point. So when you are fixing your GM, you will fix it from your bias point of view. Okay, so this is your GM Y21 and Y22 dou ID over dou VDS VGSQ times VDSQ is equal to your GDS. So your Y21 is your GM, your Y22 is your GDS, and your GDS is nothing but your 1 over RDS. And you can say that RDS is nothing but 1 over GDS, and we actually write it here. Okay, and just remember that this GM is your hallmark of a transistor. Very important thing. Okay, now if we have our thing like something uh, channel length modulation and other non-linearities, we can also work with them, but for calculation simplicity, during architecture development from scratch, we will ignore non-idealities like CLM and other thing, so we can add the effect after the derivation of the architecture. Okay, so now the thing is, uh, what is the constraint of small signal approximation for a single MOSFET? Okay, suppose your lambda is not equal to 0. So what can we do? So in previous page, we say that our this linear term VGS dou ID dou VGS is greater than all over the higher order terms, and we can just ignore the hot terms. Okay, so now we will work on this and see what the constraint that will help us to ignore all of the higher order terms. So let's see. So number one, our VGS and dou ID dou VGS over VGSQ VDSQ is greater than what? Your small signal VGS square by 2 factorial dou square ID dou VGS square VGSQ times VDSQ. Okay, nice. So now we have to compare these two things. Okay, so now we have some VGS dou ID over dou VGS VGSQ VDSQ. So now from here we can say that here is a VGS, here is also VGS. Okay, here is dou id dou vgs vgsq vdsq. So this is nothing but your uh, you can say what is this thing. Just simply write like this dou id over dou vgs. You can write it like beta vgs minus vth with 1 plus lambda vds. Okay, so here we can you can also write like this beta times 1 over lambda vds. Okay, this is your vgsq, and we can say this thing is greater than this thing. Okay, so this thing is actually your gm mu and cx wil vgsq minus vthq. You can work on this how this quantity comes beta vgsq minus vth. Okay, but I can give you a clue here. Your ID is nothing but half mu and cx wl vgs minus vt square. Just differentiate it with respect to vgsq and you will have this beta times vgsq minus vth. Okay, uh, in the presence of CLM. Okay, so now we can simply say that this thing, okay, goes on. And now if we have VGS here, let's see VGS here, and here we have VGS square 2 factorial means 2, and your VGS is equal to VI. You can simply tell that your VI should be less than twice time of VGSQ minus VTH. And if your Vi is a sinusoidal wave, then you can write it like that Vp sine your peak voltage. Okay, and you have some omega twice pi ft. Okay, so Vi is a function of t. Okay, it is a function of t. So now your peak voltage is look like this. This is Vp and this is your another Vp. So uh, you can say that your maximum VGS is equal to Vp. Okay, so VGS max is equal to 2 Vp. Your maximum VGS peak to peak voltage is 2 Vp. So you can say that your VGS max should be less than twice time this VGSQ minus VTH, and this VGSQ minus VTH is your overdrive voltage VOV. So you can simply say that your small signal peak voltage should be less than your overdrive. Okay, you have set in your bias. Okay, in your bias picture you will set your overdrive, and after that you will apply your small signal, and your small signal peak voltage should be less than your overdrive to consider the small signal as a small. Otherwise what will happen? Otherwise you can't otherwise you can't small you can't approximate your small signal model like this, and this small signal model will not be valid. Okay, and you have those higher order terms present in your MOSFET, and after your simulation you will see something like some non-linearity. Okay, so we already know MOSFET is non-linear and we want those non-linearity, but uh, for faithful amplification we didn't want those non-linearity, we want linearity, and linearity is our ultimate goal. So to have those linearity we have to apply a signal that is small for this MOSFET, and this is relative. Okay, this is relative to your overdrive. Now we'll see some cadence thing, how to plot your uh, region. Okay, and one thing I should want to mention that uh, we often write our small signal model for uh, saturation region, but it does not mean that you should uh, always say that small signal model is appropriate for saturation region. A small signal model is appropriate for any region. Okay, because we have started our equation from f of VGSQ VDSQ. ID is a function of VGSQ VDSQ. It is true for this equation 1 plus lambda VDS, this saturation equation with CLM. It is also true for your triode region equation. Okay, you already know your triode equation. So you can approximate your small signal model for any region. Okay, so I can say that a small signal, your small signal model is valid for all region. Okay, so what is the constraint on validity? The constraint on validity is your signal should be small, okay, relative to your overdrive voltage. That's the thing. Okay, so now we'll do something. How can you uh, identify proper region of operation for amplification? Let's see how can you do that. Okay, so from small signal model we can also write small signal for the model for linear region. Okay, so let's try for linear region or your triode region. Okay, so what is your y11 dou IGS over dou VGS? It is actually 0. Y12, it is actually 0. What is your y21 dou ID over dou VGS? So you already know your triode equation. Just uh, uh, differentiate it with respect to VGS, then you will have something like that mu n CX W by L VDS. Okay, for the timing I'm doing it for you, like this is your ID mu n CX W by L VGS minus VTH whole square times VDS minus VDS square over 2. So this is your triode region equation. Now I will do a differentiation with respect to VGS of this ID. So dou ID over dou VGS. So we are doing differentiation, partial differentiation with respect to VGS, but we have VDS. So VDS is constant for us. Now, so this thing will be 0. So what about this VDS? So this VDS is also a constant, and we have this 2 times VGS minus VTH. Okay, so now we can say that mu n COX, this is also constant. W by L, we have VGS minus VTH times VDS. Okay, so you can simply like write this mu n COX W by L VDS. So this is your GM for your triode equation, mu n COX W by L time VDS. So what about Y22? So for Y22, you can similarly find that your Y22 is mu n COX W by L VGS minus VTH minus VDS. Okay, so now we can see that our Y21 is depending on your second port voltage VDS. Okay, so let's do this for our saturation region or flat region. For saturation, your Y11, again your Y12 is 0. Okay, we are assuming ideal thing. Okay, Y21 is nothing but your mu n Cx W by L VGS minus VTH. Okay, so we can write like this. So this is mu n Cx W by L VGS minus VTH. We can simply put on this VDS is equal to VGSQ minus VTH, and then your MOSFET in saturation. So the same formula, but the thing is your GDS in saturation is less than your GDS in triode. Okay, so we want our Y22 as small as possible. So we are going for saturation region to be an amplifier. Again, your GM in saturation is greater than your GM in triode region. So from here we can also say that we want our Y21 as large as possible. So we can say that we can go for saturation region. So that's the thing. So let's draw a curve for this Y21 and Y22, or your GM and GDS. So we are taking blue for GM, or your Y21. So suppose this is your second port voltage VDS. Now, and this is a voltage called your overdrive VGS minus VTH. Okay, this is VGSQ. Okay, so this is the boundary. So when your VDS is less than that voltage, your VGS is less than that voltage, your GM is proportional to this VDS. So this curve will look like y is equal to mx, straight line through origin. Okay, so we can write like this, and after that your GM is constant and not depend on this VDS, mu n Cx WIL VGS minus VTH, and this value, this is the value. Okay, so here your GM is constant. So now for GDS Y22 we can say that this is your GDS Y22, and we want less value for your GDS. Before this VGS minus VTH, we have our GDS look like this, straight line, and after that your GDS will be vanish. Okay, because in that we can, for saturation region without any CLM, we can say that our Y22 is 0. But here we have our Y22 BGS minus VTH minus VDS. So this is like y is equal to mx plus c. Okay, and your m is minus here, your negative slope, and this is your Y22. This is your Y22. So actually we want this region. This is saturation, and this region is triode or your linear region. So thanks for staying with us for all over the theory lecture. Now we'll see how we can plot the region in the cadence and the effect of sweeping the voltage VGS and VDS. So let's see. Okay, let's see here. So this is our setup from previous lecture. Now we'll just let me quit this thing. Okay.